Okay, let's look at the second part of the wave behaviour of light topic and look at the interference of light. So this stuff will build a little bit on what we did last year, looking at particularly sound waves or waves in general and the wave model, but probably focused a little bit more on sound waves. But this year we're really going to probably focus, well, we are going to focus much more on light, as opposed to where the focus was more on sound last year. Let's get into it. Okay, so let's start off by looking at what monochromatic light is, what coherent light or coherent wave sources are, and looking at these terms in phase and out of phase here. So monochromatic, mono meaning one. When you do a mono on your bike, you ride it on one wheel. Chromatic is often used as another word. I think it's from the Latin for colour. So mono means one colour. Monochromatic light is composed of a single frequency. So if we think back to the electromagnetic spectrum in the last video, each colour has a unique frequency and a unique wavelength. So where we have monochromatic light, it's just composed of one frequency, therefore one wavelength, therefore one colour, therefore one amount of energy. We'll get more onto the energy stuff later on, but I did mention that when we talked about the spectrum. So coherent light also firstly must be monochromatic, but there also must be a constant phase relationship. So generally when an object, even if it emits monochromatic light, if you recall from the last video, electromagnetic waves, including light, are generated by an oscillating charged particle, so it's usually an oscillating electron within an atom. So even if that atom is vibrating at a constant rate, so therefore we get a single frequency of light released, that light will be released at random times and in random directions. So the light will be going all different directions at all different times. There won't be this, what we call this constant phase relationship. Coherent light has coherent wave sources, are wave sources that maintain a constant phase relationship with each other. They therefore must have the same frequency. So I've already said that. So this here sort of demonstrates what coherent light would be. Whenever one is releasing a peak, the other one is releasing a peak. When others releasing a trough, the other one's releasing a trough, and so on. So we have this constant relationship between the peaks and the troughs in the electric field in that electromagnetic radiation. That is what we mean by coherent. Incandescent light. Now, incandescent light, not so common now, but previously that was the old sort of light bulbs that had the filament in that we got really hot, and they just got hot. As they got hot, all the atoms in there vibrated faster and faster and faster as those charged particles in the atoms, the protons and the electrons, vibrated. They released light, and that's hence why we saw light being emitted from a very hot object. We'll again explore that in a little bit more detail later on. But because we have basically in those hot, particularly dense objects like a wire filament, there's basically a random variation in the frequencies that the particles vibrate at. They're all going in different directions. So the light is generally not monochromatic, and there's also no constant phase relationship between that light. So now we've established hopefully what monochromatic light is and what coherent light is. We want to look at what happens when we get the interference of light. And in particular, we want to gain an understanding about constructive interference and destructive interference. And these both rely on the principle of superposition. We've already looked earlier in the year about the principle of superposition. That's the principle that basically said, if there's two forces in it, if two objects are exerting a force on a third object, then the total force on that object will be the sum of the vector sum of the two forces from the other objects. Or with electric fields, if we have three charges, two charges will create an electric field. The net electric field on that third charge will be the vector sum of the electric field from the other two charges. Similar principle here. which basically says if we have two waves that are in phase, like this, when they interfere with each other, and by that, when they basically travel through the same space, we will get basically the superposition. So what we will see is we will get a wave produced in this simple case that would have twice the amplitude. Because if we add up the amplitude of that one there and there, we get that. If we add up the amplitude of this one here and here, we get this trough at the bottom. Here and here, the two peaks, we get this double peak, double the height at the top. So when the waves at a point are in phase, the resultant amplitude is the sum of the individual amplitudes. This is referred to as constructive interference. Now, if the waves are out of phase, so if when this one is releasing a trough, this one is releasing a peak, or when this one has a peak, this one has a trough, what we would see if we basically add those together, we've got a negative here and a positive, so they'll cancel out. We've got a positive here and a negative here, they'll cancel out. So basically everything there will cancel out, and basically we will see destructive interference. So basically we would not see any light. Those two light would cancel each other out. And yeah, what it says here, I don't particularly like the way I've worded this here. When the waves at a point are out of phase, the resultant amplitude is the difference between the individual amplitudes. This is referred to as destructive interference. I think I could have said that better than the difference between the two amplitudes. Basically, the two amplitudes cancel each other out, so the net amplitude is zero, so we have destructive interference. So what we're going to go on now is look at some situations that create constructive and destructive interference and some of the phenomena that we can then observe from light because of that interference. Let's continue. So let's start by looking at two-source interference. If you haven't already, I would strongly encourage you go to this PhET simulation and just have a play around. You can play around with both light, with sound waves, and with basically water waves in a simulated ripple tank. If you've used a ripple tank before, this is basically modelling what you see with a ripple tank. If we get a chance, we might look at a ripple tank in class. But I'd also encourage you, maybe even if you just want to have a look on YouTube, some videos of ripple tanks. The simulations, I must admit, often look better than the actual ripple tanks. But hopefully, just by the way I'm going to go through this, you can explain it. You can make sense of what's happening. So what we're dealing now with is when we get two monochromatic light sources, or sorry, not necessarily light sources, two monochromatic wave sources, and when we get interference between the two waves, what do we see? So this diagram here is supposed to simulate, we've got one source of waves here, let's just call that S1, and another sort of waves being generated here, S2. And as these waves are being generated, basically these lines, the solid lines are meant to indicate a peak, the dotted lines indicate a trough. So if we were to sort of draw each of these sources releasing a wave, where we've got a, whoops, I'll just do that a bit neater than that. Where we've got a peak, we'd see a solid line. Where we've got a trough, we'd see a dotted line. Where we've got a peak, we see a solid line. Where we've got a trough, we see a dotted line, and so on. And so if we looked at that, and if we set this scenario up in a ripple tank, or in the simulation, the PhET simulation, you can set that up above, what you would see is, if we looked at that, down, if you like, the middle, for lack of a better term, down this line here, you would see what we call constructive interference. Because if you look here, we get a peak meets a peak, a trough meets a trough, a peak meets a peak, a trough meets a trough, a peak meets a peak. These are all in phase. If if we go back and think of that in phase before, whenever these waves meet, they are in phase. A peak is meeting a peak, trough is meeting a trough. So because they're in phase, we get constructive interference. If we come out a little bit further along here, we see peak from source 1 will meet a trough from source 2. A peak from source 2 will meet a trough from source 1. So along this line, we would see deconstructive interference. And then if we came out a little bit further, we can see along this line, we have got peak from S1 meeting a peak from S2, a trough from S1 meeting a trough from S2, a peak from S1 meeting a trough from S2, a peak from S2 meeting a trough from S2. So again, we would get constructive interference. And if we went over this side, we would see that same pattern. So we would see basically this pattern, say if this was in the ripple tank with the waves, where we would always either have flat water where there was deconstructive interference, or we would have the larger amplitude waves where there was constructive interference. That's what you would observe. Have a look on that simulation if you haven't seen that before, and if we get a chance, we'll have a look at that in class as well. So we can be a little bit more mathematical about how we consider that path difference. So let's say if we pick, and it doesn't really matter, let's pick this point here in green first. The distance travelled by that wave front there is 1, 2, 3 wavelengths. So we would say 3 lambda. Lambda is what we use for wavelength. And over this side, this one has gone 1, 2, 3, 4. So we've got 4 wavelengths. So in this case here, the path difference between how far those 2 waves travelled is equal to 1 lambda. So that's equal to a whole number of wavelengths. So we've got basically that there is our m value, and in this case it's an integer. So that is going to lead to constructive interference. Constructively interfere when the path distance from the source to the point is m lambda. I'll say later on where m is an integer. However, let's consider maybe over this side a spot. Let's pick this spot here, and we can see that wave there travels 1 to 2.5 wavelengths. And from S1 we go 1, 2, 3, 4 wavelengths. So in this case here, the path difference is equal to 4 minus 2.5, which is equal to 1.5 lambda. Probably should have put wavelengths on those as well. And therefore, that is an example of m plus a half, where m is an integer, so 1 plus a half. So in this case, they would destructively interfere because the path difference from the sources to the point is m plus a half lambda. So they're half a wavelength out of phase. We'll explore this in even a little bit more detail in the next slide. But hopefully from that, you have an understanding of what an interference pattern looks like from two wave sources that are in phase, S1 and S2. So they're both producing peaks and trough at the same time. And then we will explore this, particularly what it looks like for light, in a little bit more detail in the next slide. Let's continue. Actually, before we continue, there is one little thing we just do need to clarify, and that's the concept of diffraction. And diffraction is essential to establishing interference patterns, particularly with light, but it occurs for any waves. So diffraction is, where's my pointer? The spreading out of plane waves as they pass through an opening, the spreading out of plane waves as they pass through an opening is an example of diffraction. This is most noticeable when the opening is comparable in size with the wavelength of the waves. So I've taken that straight out of the old curriculum statement. Probably I would have been better to say that where you have light going through a slit, like in this top diagram here, or past a sharp edge, it will cause that light to spread as it comes out from there. And this spreading is going to be essential to allow light from two different sources to overlap with each other so we can get an interference pattern. We'll see that in the next slide. So maybe just to explain what that looks like in a lab, if I took a laser pointer, I'm just using my laser level here, and I shine that past a sharp edge, can't really see in this diagram, so I turn the light out and blew it up. What you see is it causes that light to be spread out. If we just shone that laser straight at the bit of paper and there was no sharp edge, we would just see like a single red dot. But what happens is when that passes the sharp edge here on the laser pointer, it causes that light to spread out. So that's all the understanding you need of diffraction for this course. And this diagram sort of shows that light as it goes past the sharp edge, spreading out. Now, an aperture basically effectively have a sharp edge this side and a sharp edge this side, so that causes the light to spread out also as it passes through there. That spreading out of the light is going to be essential for us to establish an interference pattern with two light sources, which we'll explore now in the next slide. Okay, so firstly, when you look at this sort of main diagram on this page, hopefully you see this bit here looks a lot like what we just drew on the other page, but just sort of has the top half of this source. And that there's good reason for that, because we're just trying to build on what we've done before, but extend it to the case of what's happening with light. So what we are doing here is we are taking coherent light, and that coherent light can be generated in two ways. We can either have coherent light because we are using a laser. Later on in the course, we'll explain why light generated by a laser is coherent. But for now, you can either get coherent light from a laser or, as it says at the top there, monochromatic light can be made coherent by passing it through a single slit. So this statement here basically aligns with what we can do here. So we can use a single slit. We normally now have access to lasers in the lab, so we don't tend to use a single slit. I must admit, when I went to school and we didn't have access to lasers, we'd usually use just a monochromatic light with a single slit to produce coherent light. Now, so we've got light starting at the bottom here, and we are shining that light through two little slits. And these two slits are going to act as two light sources in the same way as we had that two source before. So we can think of this as S1 and S2, the two sources of light. Now, as this light goes through the two slits, it will spread out due to diffraction, which I just talked about before. Now, the reality is of diffraction that you're probably not going to get diffraction, well, you won't get diffraction going all the way around to 90 degrees. And this diagram is obviously not drawn to scale. In reality, we would say, oops, let me just undo that. In reality, oops, still getting the right pen. In reality, L here, which didn't come out on the diagram, which is the distance between the slits and the screen that we're shining it on up here. Like, think of that diagram. No, I haven't shown you that diagram before. I'll show you what this looks like again in a second. Oh, sorry, think about that laser shining past the edge of the razor blade to the screen. That's the sort of scales here. But this L here would be much, much greater than D, but we're just trying to make this look simple. So back to what I was going to say. In terms of diffraction, as it passes through, oops, sorry, press something I didn't want to press there. As it passes through, the reality is the light's probably just going to spread out, sort of a bit like this. And in this area here, I don't want this to be too dark, so I want to draw some other stuff here. We're going to get light from those two sources overlapping, and where that light overlaps is going to establish this interference pattern. Let's say that was going out like that. My bands go further, but that's okay. We'll come to that in a minute. So that is two sources. These two sources are light. The coherent light, so there's a constant relationship between the peaks and the troughs, and this is going to set up our interference pattern. So again, if we look at almost, this is exactly what we did before, I realise, but let's do it anyway. If we looked at this point here, which is straight ahead, we can work out the light travels exactly the same distance from those two sources. So what do we got? 1, 2, 3, 4. It's carried 4. So in that case there, the path difference straight ahead is equal to 0. And so what we would see there is constructive interference. So in a minute, I'm going to use, oops, wrong colour. I'm going to use one that we've done in the lab with a red laser. So these bright areas here you would see as red areas of high intensity, and the black in between indicates where there's low intensity light. However, if we came out a little bit and we try and use red here, so we came out to say along this point here, we could see the path difference here is 1, 2, 3, 4, and then the path difference, or the path length from here is 1, 2, 3.5. So in this case here with the red, the path difference will equal a half number of wavelength. So we'll see a dark band, we'll see an area of low intensity. And as we go out, we could keep creating those. So that explains why when you shine coherent light through two slits, you will get a pattern that looks like an area of high intensity, low intensity, high intensity, low intensity. I will show you this in a sec so you can get a feeling for what it looks like. If we wanted to, we could sketch the intensity versus basically the distance along this screen. So here, high intensity light, here, low intensity, high intensity, low intensity. So that's how basically a sketch of the intensity versus the width would look. So just for completion, D here is the distance between the two slits. Delta Y is the separation between these fringes here, and not so much between the fringes, but between two light fringes or two dark fringes, delta Y. L I've already talked about, it's the distance between the slit and the screen. And M lambda is the path difference, which is what we were talking about here. Now, previously we used to have to derive these relationships. We don't need to derive them anymore. But what you do need to know to analyse these, and we're going to do a question on this as well in a minute, but you need to just remember that the two main relationships are d sine theta equals m lambda. So basically, if we want to know at some angle, so let's draw that there is 0, at some angle here theta between those two lines, d sine theta, d down here equals m lambda. So basically for that one there, that would be d sine theta would equal a half lambda. That would be destructive interference. When I do a question, I think that'll become more obvious. And the other thing you need to know is that the fringe separation on your screen will be equal to, given by delta y equals lambda, which is the wavelength of the light, times by L, the distance between the slits in the screen, divided by D, which is the distance between the slits. Again, we'll have a look at a question with this in a minute. So, hopefully now, let's just double check, we can do everything the SACE board says we need to know, or we know everything the SACE board says we need to know, and we can do everything they want us to do. Young's double slit experiment can be used to demonstrate the wave behaviour of light. The formula d sine theta equals m lambda and delta y equals lambda L on D can be used to analyse the interference pattern where D is the distance between the slits. Theta is the angular position of the maximum or minimum. Delta Y is the distance between the adjacent minima on the screen, and L is the slit to screen distance. We need to describe how two-slit interference is produced in the laboratory using a coherent light source or using a single slit between a light source and a double slit, which is all this stuff that I explained down here, and then how that gets produced through interference here. Sketch a graph of the intensity distribution for the two-slit interference of monochromatic light. That's this here. Explain the bright fringes of two-slit interference patterns using constructive interference, this idea here, and dark fringes using deconstructive interference here. So just to go back, this is really strong evidence that light is behaving like a wave. The fact that we see constructive and destructive interference between waves that are in phase and out of phase says, well, light must be a wave. It's behaving like a wave. Later on, we'll find out the story is a little bit more complex than that. But for now, this was, if you like, the proof that scientists had that light acted like a wave. Okay, let's continue. So just quickly, this is, if you like, what the two-slit sort of experiment is based upon. We have a two-slit slide here. In this diagram, it's quite hard to see, but each of these lines actually represents, there's two slits on these wider ones. I can just see it, but it might not be coming through depending on the quality of your screen. And basically here, the two slits are furthest apart. Here, the two slits are closest together. In the two-slit experiment, we shine a laser light through two of those slits, and we see this sort of interference pattern. Again, the interference pattern is a little bit hard to see, so I've just turned the lights off, and you can see that. And you can see in the middle, constructive interference, bright band. Then we've got a dark band, deconstructive, bright band, constructive, dark band, deconstructive, then constructive again, and so on as we go across. So that is, if you like, and again, hopefully we'll get a chance to do this in the lab, but if we don't get to do it straight away, just gives you a good picture in your head of what a double slit or a two-slit experiment looks like. So the next thing, as I said I'd do before, we'll go through a question on this. The next thing in the subject outline is solve problems involving the use of d sine theta equals m lambda and delta y equals lambda L over D. Determine the wavelength of monochromatic light from measurements of two-slit interference patterns. So this question is an old exam question that covers these things really well. We've got our laser beam, so that's going to give us coherent light. It's going through two slits, and there's a screen. And it says explain the bright fringes of the two-slit separation, the two-slit interference pattern. So the key thing we want to have here is bright fringes occur where the path difference is equal to m lambda, where m is an integer. This means light reaching that point is in phase, therefore constructive interference occurs, creating bright fringes. So if I was marking that, I'd be probably giving 1 mark for realising that it's about the path difference and it has to be equal to a whole number of wavelengths. Another one for realising that basically if that occurs, the light's in phase, and then therefore that 3rd mark would be for indicating that that creates constructive interference. So if I was marking in terms of keywords, I'd be looking for something about path. Oops, I don't want to do that. Looks a bit messy. I'd be looking for the path difference, I'd be looking for in phase, and I'd be looking for constructive interference. They're those 3 main concepts that explain that. There's different ways you could do it. You could also, if you wanted, almost use that space and try and create a diagram, but I don't think that's absolutely necessary. So, part 2 of this question, the 2 slits are separated by a distance of 1.5 times 10 to the minus 4 metres. The screen is positioned 0.3 metres from the slit, so that's telling us D equals 1.5 times 10 to the minus 4. L is equal to 0.3 metres. The central part of the interference pattern observed on the screen is shown in the scale diagram below. Using the diagram above, determine the distance between adjacent maxima. Mark clearly on the diagram the measurements you have used. So I'm going to show you the good and the bad way, if you like, to do this question. Let's say the bad way to do this would be say, oh, that there is at 3 millimetres, and I'm going to go to the middle of this band here, and I'm going to say, oh, that's there. So that's 1, 2, 3, 4, 5, so that's 1.2. So I'm going to say that would be about 1.25 millimetres. And doing that as a check of your answer is not a bad thing, but experimentally we are much better to take multiple measurements and average. It's that idea of, reducing your amount of random error, because there's judging where the middle is there. So let's maybe flick to green and do this again, and let's say the middle of that one there, let's say that's at 0.4 millimetres, and I could have chosen an edge as well. And let's come up here and say the middle of that one, and I'm even going to be a little bit off here, but that won't matter, is at 5.6 millimetres. And in that space we have 1, 2, 3, 4 numbers. We have gone across 4 different bands, 1, 2, 3, 4 gaps. So the distance would be equal to 5.6 minus 0.4 divided by 4, which would be equal to 5.2 divided by 4, which would be equal to, if I've got my maths in my head right, would be equal to 1.3 millimetres. So that is a better way to do it than the way I did in blue. Next, calculate the wavelength of the red beam. So what's the information we know? We know that D equals 1.5 times 10 to the minus 4 meters, so we don't need to convert units. We know that L is equal to 0.30 meters. We've got two significant figures there, just making a little note for when I get to my final answer. We know that delta Y from the above question is equal to 1.3 millimeters. Must convert that to meters, standard unit, so that's 1.3 times 10 to the minus 3 meters. And it's asking us what is the wavelength. That is our unknown. Do we have an equation that relates all those? We do. This equation up here, but we do need to rearrange it. So we go delta Y equals lambda L on D. I'll do my algebra in a different colour. Times both sides by D. Divide both sides by L. So we get left with lambda equals D times delta Y on L, which is equal to, let's get this right, 1.5 times 10 to the minus 4 times by 1.3, sorry this is a bit messy, times 10 to the minus 3, divide by 0.30 meters, and that, if we plug it all into the calculator, equals 6.5 times 10 to the minus 7 meters. If we convert that to nanometers, we divide by, we times it by a billion, so that would equal 650 nanometers. And once you do a few of those questions, this one comes up very often. That sort of 650 range is about the range of red light, and we can see from the colour that's red light. So that's just a really good check that, yep, we've got around about the right answer. So, there are other problems you can get about that, but that just typically shows you that process of working through one of those questions. Let's continue. So now we're going to talk about diffraction gratings, transmission diffraction gratings. This time I'm going to show you the setup before I go through the theory, which in hindsight might have been better to do last time. This is a typical diffraction grating. Rather than just having two slits where light can interfere, this has basically got continuous slits all the way along. And in this case, we can tell down here, 600. This has 600 lines per millimetre. If we want to work out how far is it between lines, if there's 600 lines per millimetre, we go 1 divide 600, and that tells us how many millimetres there is between each line, but we want to convert millimetres into metres. So we've got to divide by 1,000 because there's 1,000 millimetres in a metre. So that tells us the distance between each of the lines on this transmission grating is 1.7 times 10 to the minus 6 metres, or 1.7 microns. 10 to the minus 6 metres is a micron. So if we shine a laser light through that, we see this sort of interference pattern, bright central band, and then we get these bands further out of constructive interference, which is a little bit like the two slit pattern. But what you notice now here is a couple of things. Firstly, the distance between the bands is much greater. Now that is because D is much smaller in this equation. So if we think of this equation, same equation applies here. D sine theta equals m lambda. So rearrange that a bit. Let's say sine theta equals m lambda on D. Because D is much smaller, sine theta will be much greater. So because the distance between the slits is smaller than the double slit one we looked at, this angle between where we get constructive interference will be much greater. And I'll talk about this a little bit more in a minute as well, but I think that's worth noting. The other thing you'll note is that we have quite narrow high intensity beams, and then we have large regions of low intensity between them. Whereas in the double slit pattern, we had basically equal size bright, dark, bright, dark. And I'll explain as we get in the next slide why that happens. But this is the picture you want to have in your head for using a transmission grating, diffraction grating, at least to start off with. Let's continue. So I've already said a transmission diffraction grating consists of many very thin, equally spaced parallel slits. The interference, and so this is just the pattern from exactly that example I showed you before, but I've just turned the lights off so you can see it a bit clearer. The interference of the light from a diffraction from a grating results in a pattern consisting of very narrow, intense maxima separated by regions of negligible intensity. So if we were going to do one of those graphs with basically intensity on this axis, we would go, oh, we've got a little bit there, then we've got nothing, and then we've got a little bit more there, nothing, big bright bit there, nothing, a little bit like that, nothing. And you can hardly see it on this one, but there's a little bit there, and so on. So that's what that intensity distribution would look like, and I'll explain why we get that. In fact, I'll explain why we get that now, and then I'll do the proof of m lambda equals d sine theta, which is the other thing that it tells us derive. That's the other important thing we need to do. So why do we get this sort of pattern with large areas of no intensity and just these very narrow bright bands? We need to think about our diffraction grating here. It's got lots of slits in it. The slits D is much smaller than the width of the laser. So the laser might be 1 or 2 millimeters across the laser beam. It's 1/600th of a millimeter between these slits. So the laser beam is going to be hitting multiple slits at once. So because the slits are so close together, light emanating from several slits can overlap. This overlap creates an interference pattern in a similar manner to the two slit example. So the light that's coming through this one could interfere with the light that's coming through this one, or the light that's coming through this one might interfere with one right down here as well, because they are so close together compared to the width of the beam. So, yeah, if the path difference, and the path difference we can work out here, this light's all travelling away. If we draw this right angle through here, we can see this distance here represents how much further this light source, or the source from this slit, will travel compared to this one here. So if this one travels half a wavelength further than this one, then we will get destructive interference between these two. So we will get, basically the light will cancel out, we won't see intensity. The only time we'll see constructive interference is if this distance is a whole number of wavelengths, and then this one will constructively interfere with this one. So yeah, if they're half a wavelength out of phase, these two will destructively interfere. But if they're a quarter of a wavelength out of phase, well, this one here will be a quarter of a wavelength different from this one, but it will be half a wavelength different from this one down here. So this one here and this one here will be half a wavelength out of phase. So this one here will destructively interfere with this one here, and this one here would go with this one. So we would see destructive interference. If they were, say, 1/8 of a wavelength out of phase, that would be 1/8, 2/8, 3/8, 4/8. 4/8 is equal to a half. So the one from down here would destructively interfere with the one from here. They would cancel out and we would see destructive interference. It's only when this path difference is equal to exactly a whole number of wavelengths that we will see this constructive interference like we see here. So how have I written that? However, because the slits are so close together, D is very small, the angle of reinforcement is much larger. Sine theta is proportional to 1 on D. So that's why they're so much further apart that I talked about briefly, because D is smaller, sine theta is greater. As the second part of this, as light from multiple slits can overlap, even if light from the first and second slit is only 1/10 of a wavelength out of phase, light from the first slit will overlap with light from the sixth slit down, so 1, 2, 3, 4, 5, and destructively interfere, because it would be 5 1/10 of a wavelength. 5 times 1/10 equals a half. So that one would be out of phase with that one. We would get destructive interference. Constructive interference can only occur at an angle where diffracted light is exactly in phase, i.e. the path difference is equal to m lambda, where m is a whole number of wavelengths. This results in an interference pattern containing sharp, high-intensity maxima at large angles, surrounded by regions of negligible intensity, all these regions here. So that is most of what we need to do, but the other important thing that I haven't done is derive this d sine theta equals m lambda formula, but with a very basic knowledge of geometry, you should be able to do that and hopefully understand that fairly easily. So what we have here is this here, obviously, is the angle theta. Now, if this angle in here is theta, this angle down here is also theta, because if you're doing geometry, you could say they're mutually perpendicular. This line is perpendicular to this line. So, sorry, that line there is perpendicular to that line there. And this line here is perpendicular to that line there. But in physics, you don't even need to state your geometric reasoning. You just need to realise if that angle there is theta, you can put a theta there. Then we can just use our SOHCAHTOA, but we only need to use the SO, which is basically sine theta, which is that green theta that I've just written, is equal to the opposite over the hypotenuse. And in this case, the opposite is our path difference. And our hypotenuse is this distance here between slits, which is D, that's the long side of our triangle. So we rearrange that relationship there and we get sine theta, we usually put the D first, D sine theta is equal to the path difference. So I left myself a bit short of room here. If path difference equals m lambda, we would get constructive interference. So that's a bit messy. And obviously, if path difference is equal to m plus a half lambda, we would get destructive interference. And I've run into my border on my page, so it doesn't want to write. But yeah, sorry that's a bit messy, but I think you can get the idea of that. I'm not going to read through again all of those, but if you do have a scan in your notes that I've given you, you should see that in talking about all that stuff, I have covered all of that stuff there. So I think we only have one thing left to do, and that is to talk about one of the really important applications of transmission gratings, and that is spectroscopy, and relate the importance of it for spectroscopy to some of these properties that we've just discussed in this slide. So in very simple terms, spectroscopy is the idea of analysing a light source to see what colours it's made up of. So we can do this in the laboratory. We've got little spectroscopes that we can shine at different lights and we can see what colours they're made of. And we'll probably do that at some point, and you may have already done that hopefully as well. So here, this would be the spectrum of white light. White light is made up of all the colours mixed together. So if you looked at the spectrum of white light, you would see all the colours. This here is an example, say, of an emission spectrum from a gas, which just releases red, yellow, green. So we would see which individual colours are released. We'll talk about how emission spectrum are produced when we look at the structure of the hydrogen atom in one of the later subtopics. Here is an example here of an absorption spectrum where we shine white light through, say, a certain gas, and it absorbs some of the wavelengths of the white light, and we see those bands removed. This is one of the ways we analyse stars to see what gases stars are made of. Again, we'll talk about that a little bit more later when we do the hydrogen atom, the structure of the atom, structure of the hydrogen atom subtopic. So spectroscopy, though, is this idea of how we analyse a light source to see what colours it's made of. We can not just analyse visible light sources using the right equipment. We can analyse X-ray spectrum, we can analyse UV spectrum, we can analyse infrared or radio wave spectrum, and see, look at some signal and see what individual wavelengths or frequencies or energies that light is composed of. It's a really important technique in science. We can basically make a fairly simple spectroscope in the laboratory using a transmission grating. I've lost my original photos of these. I've had to pull these out of my old notes, so they're not quite 100% clear, and they've got already some writing on them, but hopefully you get the idea. If we take here, and I've just used a desk lamp here, and we shine it through this tube here, and this tube has a very narrow slit at the start, which helps to basically get the light coherent as it comes through. And we shine it in here, you can hardly see it, but there's a transmission grating. And then as this white light goes through the transmission grating, depending on the wavelengths that are made up for, they will constructively interfere at different angles because, sine theta equals m lambda. So the angle of reinforcement, theta, is proportional, or the sine of the angle of reinforcement is proportional to the wavelength. So different wavelengths, i.e. different colours, will reinforce at different angles as we move this tube around. So if we go at 0 degrees, so we have this going straight through along this blue line, we just see white because all light, all colours will constructively interfere at 0 because the path difference will be 0 wavelengths, so a whole number of wavelengths, an integer number of wavelengths for all of them, and we'll see white light. But then as we spin this around, and this isn't a very good photo, but you can almost see this rainbow spectrum appearing here as I'm shining white light through. And what we will build up is this sort of picture like this continuous spectrum that shows you all of those colours that the light's made up of. Again, we'll show you an even simpler spectroscope in the lab, hopefully. However, why are transmission gratings very useful for spectroscopy? Firstly, because of the small d, the small distance between the slits, we get very large angular deflections. So that the angle that blue reinforces at will be significantly different for the angle red reinforces at. So it really lets us separate out all those colours that make up a bright colour and see them individually. We also see quite sharp maxima. So if we've got something that's emitting at this frequency here, or this frequency here, we'll see them as quite distinct narrow lines. And we won't see sort of large areas of constructive interference for these colours because of that fact that, adjacent slits, the light goes across many adjacent slits, so you only get constructive interference when the path difference is a whole number of wavelengths. Even if you're a little bit off being a whole number of wavelengths, then you will get cancelling out from slits further down or further along the transmission grating, so you'll get a very low intensity. So basically these factors make it easy to measure and accurately determine the wavelengths of light being analysed in a spectroscope. That's why a diffraction grating is a very useful tool for doing spectroscopy or analysing the frequencies or the wavelengths or the colours that make up an individual light. So that's it for the wave behaviour of light topic. There's a little bit there to get your heads around, but yeah, please sing out if you have any questions. If you like this video, click like. If you want to see more of this great stuff, click subscribe. Cheers.